Yesterday we took that next step from the fact that we have charged objects to how do we get charged objects. There were two ways that we identified yesterday of charging objects. What were those two ways? Charging by, Daniel? Maddie? Induction and conduction. Good. Charging by induction and conduction. Now, there were a couple fundamental differences between the way that conduction and induction take place. Conduction always involves what? What always happens when you have conduction taking place, Simon? Good. There's a transfer of charge. And by the way, if charges are going to transfer, and they do sometimes, certainly within conduction, what charges are going to transfer? Is it going to be the protons? Going to be the electrons? Good. So electrons will always transfer within conduction. What about with induction? Do electrons transfer in an induction? Emma? No, never. So we always have electron transfer with conduction. We never have electron transfer with induction. One of them usually involves two things touching each other, although not always. Usually involves two things touching each other. Which one usually involves touching? Maria? Good. And which one never involves two objects touching each other? Induction, of course. Right. Good. Now we break conduction down into two subcategories. They're charging by friction, charging by contact, or sometimes we just call that subcategory charging by conduction. Charging by friction simply involves rubbing two things together. You rub two things together, one of them gains electrons, one of them loses electrons. Let's say that they were both plus 5 coulombs when I started rubbing them together. Okay, they were both plus 5 coulombs when I started rubbing them together. One of them became plus 3 coulombs. What's the other one become? Plus 7. Okay, that's governed by the law of conservation of charge, right? If we had plus 5 and plus 5, the total was plus 10. Rub them together, the total's still got to be plus 10, but if it's plus 3, the other one's got to be plus 7. They're not going to balance out here when we're charging by friction, right? In fact, it's kind of the opposite. But the total charge still has to remain exactly the same as what it was. By the way, the one that was plus, they're both plus 5, right? The one that became plus 3, did that gain or did that lose electrons? The one that was plus 7, did it gain or lose electrons? The one that was plus 3, gain or lose? Lose electrons? Who agrees? Gain? Who agrees? All right, nobody agrees with either one of you. You're right. It gained electrons, right? If it was plus 5 and it became plus 3, it's less positive than it was before. If it's less positive, how did it become less positive? We can either lose positive, which can't really happen, right? Or you can gain negative, right, to make it less positive. Of course, the one that became plus 7 lost electrons, making it more positive. All right, the other way that we charge objects by conduction is by contact. Here we bring two objects close together, touch them together, or bring them close enough where charges actually jump from one to the other. This is when they want to balance each other out. Okay, this is the example that we've been looking at the last couple of days, right? Touch something that's minus 5, something that's plus 5, they balance out to be 0 and 0. Touch something that's plus 10, touch something that's plus 12, they balance out to be plus 11 and plus 11. Hey, let's ask that question again, Tom. Both, one of them was plus 10, one of them was plus 12. They both become plus 11. The one that was plus 10 and became plus 11, did it gain or lose electrons? Good. It lost electrons because it became more positive. Good. Charging by induction now. Two subcategories of that. We have a temporary separation of charge, and then we have the permanent charge. And they kind of go together in the sense that once we get the temporary separation, we just add some little thing to it, and it becomes permanent. Let's draw a couple diagrams here. All right, we got 4 positives or 4 million positives there. We got 4 million negatives scattered around there so that it's a neutral object. We bring, let's say, a negatively charged object nearby. What's going to happen to the protons within that neutral object when we bring a negatively charged object nearby? The protons? No. What's going to happen to the protons? Kirsten? They're going to stay where they are. As long as we're in a solid, We talked about this with Simon yesterday, right? He asked a good question. As long as we're in a solid here and the atoms themselves can't move, then the protons aren't going to go anywhere. They're going to stay where they are. And as far as the protons are concerned, this is going to look exactly the same. What's going to happen to the electrons in there, though? The electrons are going to move around, right? They can move around a lot easier than the protons can. Where are they going to go? Oh, you better know this. Haley? Yeah, they're going to go to the left-hand side. Not necessarily all of them. We're going to draw it as if all of them go to the left side. But they don't all have to go there. We get a preponderance of them going there. Take a look at the left-hand side here. Maybe we have some positives on the left-hand side, but we still have more negatives than positive, leaving that side negatively charged and the other side positively charged. Notice the side that's closest to the charging object, okay, this side and the charging object are oppositely charged. That means that they're going to attract each other. That's why charged objects attract neutral objects. Here we got another neutral object. This time we're bringing a positively charged object nearby. What happens to the protons here, Tom? They stay where they are. What happens to the electrons there, Daniel? What happens to the electrons? They go to the right. Or at least lots of them go to the right, so that we have a net effect of the left side being positive and the right side being negative. And we got positives and negatives scattered all throughout, but we have more negatives on the right side and more positives on the left side. Take a look at the side of this neutral object that's closest to the charging object. They're oppositely charged again. That's why charged objects attract neutral objects. All right, this is temporary, because when we take this thing away, what happens? Just go back to where they were before, right? How do we make it permanent? How do we make this permanent? Sorry, Ken? Tape them? Did you say? No. Unless your tape contains, unless your tape contains some kind of conductor and is taped to the ground. In other words, unless we add a ground wire to it, then that's not going to work, right? Where exactly did that one come from, Ken? All right, we attach a ground wire to them, right? The ground wire literally will carry electrons to the Earth or from the Earth or some other big object. It doesn't have to be the Earth, right? We talk about it as grounding, and in England they actually refer to it as earthing. I don't know if you guys have ever heard that or not, but in different parts of the world we call it something different. It's the same thing, grounding or earthing or whatever the case may be. In the end, it usually goes to the Earth, hence the term earthing. But it doesn't have to. If we have some massive object that this ground wire down here is attached to, well, then that can serve the same purpose as the Earth, providing a source or a sink for electrons to come from or go to. And usually it's the Earth, though. All right, so what happens? Nothing happens to the protons, right? What happens to the electrons in the first diagram when we're bringing the negatively charged object nearby? Electrons are going to go through that ground wire, right? Which way, though? Down or up? They're going to go down. They're going to be pushed as far away from this guy as is possible. So now these negatives that got pushed to the left-hand side, they just keep going. Now they keep going down into the Earth. Now we don't have a separation of charge over there. Now we've got a positively charged object. We brought a negatively charged object nearby. We charged it positively by pushing the electrons down into the Earth. The only problem is, as soon as we take this guy away right here, they're going to go back to where they were before. So what we have to do is cut that ground wire to cut off the path. Okay, there's the tunnel, the stairs down to the basement. Well, if we break the stairs, take out the stairs, then these guys, these electrons that went down into the ground, have no way of getting back up. So it remains positively charged permanently. Now, some people would say, that's conduction, right? Electrons were transferred down into the Earth. It's true. Electrons were transferred, and in a sense it is conduction. But the overall process we still call induction, because this is the thing that's doing the charging. And it's not transferring charge, and it's not touching the other object. So we still call the overall process induction. Take a look at the other diagram. This time, negatives are going to get pulled up from the ground or whatever big object you have down here. The electrons go in here. Now you don't have a separation of charge. Now you got a negatively charged object. Let's cut the ground wire. Even if we take this guy away now, we have no way for the electrons to get back down to the Earth where they came from. So now it's permanently negatively charged, again, by induction, even though there was electrons being transferred within that, not from this object to this object. Does that make sense? All right, what do you see there? Well, some of you may have one of these in your house. Some of you probably do, and some of you won't have one of these in your house. This is an electrostatic precipitator, it's called. The idea of this electrostatic precipitator is that it cleans the air. You got dust in the air. You got smoke particles in the air. You got little mites in the air, little things that aren't good for you, okay, pollutants in the air. We want to get those things out. There's a simple, ingenious little way of accomplishing that using electrostatics, using the idea of charging objects and like charges repel and like charges attract and so on. These little wavy things that you see right here, that's the air being blown through this electrostatic precipitator. You might see this attached to a furnace, and then the furnace fan blows the air through this precipitator. Now, that air consists of air, but also a bunch of little particles, like dust, or smoke particles, or whatever pollutants that you want to filter out of the air. They're neutral. Normally, they're neutral. They get blown through these rods, these blue rods that are sticking up. And now, I'm not sure if you can see that on the board from where you guys are sitting, but these rods are negatively charged. All three of them are negatively charged. They're negatively charged because you can see if you look closely at this battery or this power supply, the negative side of the battery is attached to them. So they become negatively charged because the negative side of the battery is there. Whereas these red plates are positively charged because the positive side of the battery is attached to those plates. So what happens now? This air gets blown first through these blue rods, these negatively charged blue rods. As these dust particles and other pollutants touch these blue negatively charged rods, what happens? What happens to the dust particles? Remember, they're neutral. Neutral touches negative. What happens? Yep. They become negative. Think of it this way, guys. We did a couple problems with this using numbers over the last couple of days. Say the dust particles are 0 coulombs. Let's say the blue rods are 5 coulombs. What are they going to want to balance out to be? Sorry, -5, I should say. What are they going to want to balance out to be? -2.5 and -2.5. Now, they may not balance out here because the dust particles are small, but they are going to take some electrons. The dust particles and the other pollutants become negatively charged. So what? Well, now these negatively charged dust particles, along with the air, keep getting blown through these red positively charged plates. What's going to happen to these negatively charged dust particles now as they go through these positively charged plates? They'll be attracted to the plates. So what doesn't go through? What doesn't make it all the way through? The negatively charged pollutants. What does make it all the way through? The neutral air, like the molecules of air. Make sense? So now you've got more or less fresh air coming out the other side to be blown through your house. Okay. Now, at some point, obviously, you're going to have a lot of dust on these plates, and what are you going to have to do? Clean it, right? That would be likely a filter or something you take out to clean. Here's another one. What are we doing now? Painting a fence. That's what you came to physics for, right? Is to learn how to paint a fence. You can paint all kinds of things, metal things. They do this using when they paint cars in factories. They use electrostatic painting. Well, we're not just firing charged particles at cars and painting them with charged particles. Well, kind of we are, actually. What we're doing here is charging paint, charging the paint droplets. You've got this this rod inside the nozzle of this paint sprayer. And this rod can be charged, doesn't really matter, either positive or negative. Okay, let's say it's negative. What happens to the paint droplets as they go past this negatively charged rod? I mean, you can imagine how you could charge that negatively, right? Electricity, plug it in and set it up so that you could charge it negatively. Okay. So what happens to these paint droplets as they go by this negatively charged rod? They become negatively charged. When neutral touches negative, then both of them become negative. The paint droplet becomes more negative. The rod becomes slightly less negative. So now you got negatively charged paint droplets going out. Okay, so what? So what? Well, you want to paint a fence, let's say. This is a simple one because it's already grounded, right? The steel in the fence is literally going into the ground already. It's grounded. Okay, if it's not already going into the ground, like in a car, for instance, then you'd want to ground it. So what happens? Where do negatively charged particles want to go? Just drew you a picture a few minutes ago. Where do negatively charged particles want to go? To the ground, right? They want to go to the ground. So what's going to happen to these negatively charged paint particles? Well, the negatively charged paint particles aren't going to physically go down into the ground. It's charge that goes down into the ground, right? But the paint particles are going to be attracted to these pieces of steel. So what happens as you're blowing the paint against this steel fence? You don't have to worry too much about painting the deck of your pool. You don't have to worry too much about paint going on this tree over there, or paint getting on that little kid that's playing in the grass next to it. Although you probably want to tell him to not play there, because the idea here is that these paint particles don't just go everywhere. They don't diffuse through the air like paint normally would, right? They get attracted to the steel that's attached to the ground. So almost all of the paint particles will do this, right? Even the ones that are missing it, what happens? They get pulled back around and paint the back side of it. What's the benefit of this? One, you get way, way, way less waste of paint, because you're not getting all this paint going everywhere else, right? Almost all of the paint is going to where you're actually trying to paint. Way less wastage. But the other benefit to it is that you can actually paint the back of it from the front. So you can paint the whole thing more or less from one side. It's so much quicker, so much less waste, and so much quicker simply because you run it over the front and you more or less get the whole thing. You might want to go over the back real quickly, but you're more or less going to get the whole thing from one side. Does that make sense? Are you going to see this or this on a diploma exam? Probably not. Neither one of those are curriculum objectives. Neither one of those are mentioned in the program of studies that you have to know. But you do have to be able to interpret and understand the laws that we've learned, charging, through the three laws of electricity, charging objects by conduction and induction. You have to be able to apply that to new situations. Okay, so I've given you a couple here that I thought were kind of interesting, and that hopefully will help you if you see another brand new one, sometime that you've never seen before. Will kind of help you work through that. Okay, make sense? I got a couple multiple choice questions for you to work on here. First one is 37. You know what, on this one, actually, I'd like you to do 37 and 38 at the same time. We'll submit this as multiple choice 1 and multiple choice 2 on the submission sheet, both at the same time, please. All right, the first question says the bottom of a thundercloud usually becomes negatively charged. So you can see that here. Not real clear in the diagram, but if you're looking at it closely, you can clearly tell that that the bottom of the thundercloud is negatively charged. Now, how it becomes negatively charged, there's actually some debate in scientific circles as to how it becomes negatively charged. Okay? That's something to do with charging by friction. Anyways, it's neither here nor there for this question. It goes on to say, before lightning strikes, the charge of the ground directly beneath the thundercloud will become what? Before the lightning strikes, before it strikes. Okay, before it strikes, is charge being transferred? No. So that must be right away. We know that that's charging by induction, right? Can't be charging by conduction if charge isn't transferred. Okay? That's good because of the 10 of you that responded, all 10 of you said either A or B. So you all recognize that it had to be induction before the lightning strikes. That's good. Now, the only question is, does it become positive or does it become negative? Well, let's draw the ground here. Here's the ground. The ground is essentially neutral. Now, if the bottom of the cloud is negatively charged, what's it going to do to the protons, Tom, in the ground? What's this negatively charged cloud going to do to the protons in the ground? You're going to leave them. They're going to stay where they are. What's going to happen to the electrons in the ground? They're going to get pushed further down, right? They get pushed down here somewhere, right? We create a separation of charge, temporary separation of charge in the Earth. So the part of the ground that's directly beneath the cloud becomes what? Positive by induction. The answer is A. Okay, and that's what 70% of you said. Good. 38. During the downward lightning strike, the charge on the top of the tree becomes what? Well, let's ask ourselves, first of all, is it conduction or induction? During the lightning strike, electrons are being transferred from the cloud to the tree. That's going to be what? That's conduction. Charge is transferred, that's conduction. That eliminates A and C right now. Leaves us with only B or D. You know what, guys? Odds are it's not going to be neutral, right? If you're transferring charge, you're not going to make it neutral. So what are you going to do here? If the electrons are coming down to the top of this tree that was neutral, presumably, then the top of the tree becomes what? Negative. Right? So the answer is negative by conduction. You guys did a good job on this one, too. 80% of you got this one right. Although the other two answers were scattered a little bit, unlike in question 37. So good job. The answer is negative by induction. All right. One more quick little thing here, guys. I just want to show you a device that you're supposed to be familiar with. We actually have some of these, but in my experience, they don't work very well. At least the ones that we have don't work very well at all. An electroscope is a device that's used to detect charge. It does not tell you what kind of charge you have. It does not tell you how much charge you have. It just tells you whether you have charge or not. Here's how it works. You bring a charged object, bring an object, okay? Forget about whether it's charged or not. Nearby the ball of this electroscope, this metal ball on the top of a steel rod on this electroscope. Here's the metal ball. Here's the steel rod. Now, at the bottom of that steel rod, you're either going to get two really, really thin pieces of foil, really, really thin. Like you look at aluminum foil and how thin that is, this is way thinner. Or two really, really light metal-coated balls that will take a charge quite easily. If this object that I bring by is positive, then the neutral ball, the neutral rod, and the neutral leaves on the end of it that are just hanging freely down all change. That's because the negatives that were in these neutral leaves get sucked up into the ball. I had an even number of positives and negatives scattered throughout this, but now the negatives get pulled up into the ball. That leaves the leaves positively charged. What's going to happen to those leaves if they're both positively charged? They're going to push away. We've just detected charge. Okay, the leaves pushed away. The leaves repelled each other. If the leaves repel each other, charge must be there. Well, it's got to be positive charge, right? If the leaves push away? Not necessarily. Here's another version of the electroscope. Works exactly the same way, though. Bring a negatively charged object nearby. What happens to the positives here? Nothing. What happens to the negatives? They all get pushed down into the leaves. What happens to the leaves now? Now the leaves are negative instead of positive. What happens to them? They get pushed away from each other. So if you bring a charged object nearby, the negatives will either leave the leaves and leave it positive, or the negatives will go down into the leaves and make them negative. In both cases, they're going to repel each other. In both cases, you've just detected charge, but you haven't indicated what kind of charge it is or how much charge you have. Does that make sense? What would happen if I grounded this? What would happen if I put a ground wire right there? Are the electrons going to go down into the ground, or are they going to come up from the ground? They're going to come up from the ground. Where are they going to go? Well, they're going to want to go right here, right? They're going to want to go as close to this guy as they can. But at some point, you're going to get enough electrons up there that they can't all stay there. So some of them will go down here. Eventually, what's going to happen is that these leaves will still spread apart, and they'll stay spread apart if you cut the ground wire, because the entire thing is now negatively charged. Does that make sense? What's going to happen over here if I ground it? Ooh, this one's a bit of a tougher one. Do the electrons go down into the leaves or go down into the ground? They would actually go as far away. It's not the leaves that they want to go to. It's far away from this thing that they want to go to. So these negatives would get pushed not down into the leaves. These negatives would get pushed down into the ground, leaving the entire thing positively charged. Now, the leaves would still stay spread apart, but this time, if I cut the ground wire, they would stay spread apart even when I take this thing away, because the entire electroscope remains positively charged. Make sense? All right. Good. Here's your homework for the weekend, guys. Look at that. Page 523. I'm being nice to you. Cutting off a whole bunch of questions. 5 questions. Let's cut off these ones too. Your homework for the weekend is page 523, questions 6 to 10. And that's it for today.